Hi, this is a video tutorial on using mineral physical properties and identifying minerals. I will be referring to a PowerPoint slideshow that is a little bit different than the one that's available for this class. It has the same information but different pictures. So, as a preview, you should have already learned about minerals for this class. What is a mineral? Minerals, you can think of them as the building blocks of rocks, but a more kind of precise way to define a mineral is that a mineral is a naturally occurring inorganic solid that has a specific chemical composition and an orderly arrangement of atoms, and another way of saying that, it has a crystalline structure. There are thousands of minerals that exist around us, and so how can we determine what mineral we're looking at? Well, each mineral has consistent, recognizable physical and chemical properties. The property tests we will be doing are dominantly physical property tests. There's one chemical property test. So a physical property test is a test that we can use perform using our five senses, mostly vision. We have different ways of looking at minerals and describing them, but there are other senses that you can use for some minerals. So they're useful or necessary to identify minerals, and the minerals that the properties that each mineral possesses depends largely on the chemical makeup of the mineral. What elements are present in what proportion, but it also depends on how the atoms are arranged, the crystal structure of the mineral, and it also depends on the strength of the bonds. You should have learned already that there are different types of bonds that hold atoms together in a solid. Some of the bonds are weaker and some are stronger. Some bonding allows the electrons to move more freely. So the types of bonding that's present will also determine the physical properties of the mineral. So some are diagnostic. What I mean by this is that for some minerals, some of the property tests are not very useful in determining what mineral it is. So it depends. You have to kind of go on a mineral by mineral basis. Like, for example, some minerals, color is really easy to tell the mineral apart. And some minerals, it comes in such a variety of colors that, or maybe it's a black mineral and there's just thousands of black minerals, so it's not a very useful property. But that property taken with other physical properties will allow you to identify each mineral. So there's lots of different types of physical properties. These are some that we will be looking at, and I will go through each one of these that you need to do in the lab. But there's lots of other properties. Some of them are only useful for a small handful of minerals. Most of these we will not be looking at. We will look at a couple of these, like magnetism and effervescence, which another way of saying that is a reaction to acid. Okay, so if I were to hand you a bunch of minerals and you didn't know anything about identifying minerals, and I were to say, describe these minerals to me, what are the properties that these minerals possess, or can you break these minerals into groups? Most people likely would rely on the physical property of color to identify or describe minerals, and that makes sense because color is something that we're used to referring to on a day-to-day basis. We have the tools to describe color. Sometimes using color is very diagnostic. For example, there are a couple of minerals that have really distinct colors, and these colors almost never vary. Let me find my camera here. There's a grouping of minerals called azurite and malachite, and so they come in these colors. And they're almost, as far as I know, they are always this color, and the colors are really distinct, so that's helpful. There's a mineral olivine that's kind of this olive green color. Where is my camera? So it's not as distinct a green color, but it's rarely another color. Sometimes yellow, but mostly it's green. But sometimes a single mineral may come in a variety of colors. As you can see in this photo here, there's a few examples of quartz. Quartz is a very common mineral. when you see quartz probably almost every day, if not every day, and often it will look like this. Sometimes it's a really nice rosy pink color. Sometimes this is kind of a smoky brown color. It can be this really nice amethyst purple color. It's kind of a more common, kind of a cloudy white color, or it could be completely clear like this. So how do you use color as a property to identify quartz? It can come in other colors that I haven't even shown you. So color is not extremely helpful for quartz. Why does quartz come in so many different colors if it's always made up of the same elements? It's always made up of silicon and oxygen. Well, the answer is that there are other elements present in trace amounts. So they're not, they're not identified when you see the crystal, when you see the chemical formula for the mineral for quartz. It's always SiO2. If it happens to have another element in there in trace quantities, it's not enough to change the chemical formula, but it is enough to show the mineral in a different color. So sometimes it's more useful to look at another way of looking at a mineral's color. What if we could kind of pulverize the mineral and turn it into a powdered form and then look at the color? Then that color would not be as influenced by trace impurities. For example, there's a mineral called hematite, and sometimes it's this kind of a rusty color. Sometimes it is kind of a what we call specular hematite, where it looks kind of glittery and silvery, and there's some other variations. But no matter what the kind of hand sample color of the mineral, if we use a ceramic plate and we rub the mineral on the ceramic plate, as long as the mineral is not harder than the plate, then it will leave a powdered streak of the mineral. So I'm going to do that here. I'm going to take the mineral and I'm going to rub it a little bit on the plate. And so we have this nice kind of a rusty brownish reddish streak left behind by the mineral. So as you can see in this PowerPoint, so even if the hematite is kind of more of a silvery color, if you streak it, it has a diagnostic reddish brown streak. Some minerals, the streak is the same as the color of the mineral. We say that's congruent, but sometimes the streak produces a different color than the color of the mineral, incongruent. For example, there's a mineral chromite. In hand sample, it's a black mineral, but if we rub it on the plate like this and produce a streak, look at the streak, it's a greenish brown color. So that can be more helpful than color in identifying minerals. Another property of the minerals, another visual test, is something called luster. And luster does not refer to the color of the mineral. It's the way that a mineral scatters light. So solids to different degrees will absorb light or reflect light, meaning that when the light hits it, it bounces off kind of in one direction, or it scatters light, meaning that the light kind of bounces off in random different directions. So there's a lot of different ways to describe luster, but there's two main categories of luster: metallic luster and non-metallic luster. So when you look at a mineral and you want to determine the luster of the mineral, the first thing you ask yourself is, does it look like a metal? For example, this is pyrite. It has a metallic luster. I don't know why I can't find my camera here. Metallic luster. If it has a metallic luster, you can stop there. Here's another example of a mineral with a metallic luster. Okay, so what if the luster is not metallic? What if it looks maybe like this? Definitely not metallic. We say it's non-metallic, and then we don't stop there, because if it's non-metallic, well, maybe it reflects light like glass, and so we say it's non-metallic glassy. Another way of saying glassy is vitreous. So that's a non-metallic glassy luster. But maybe it's not metallic, but it doesn't really look that glassy. Maybe it looks kind of more pearly or satiny in luster, the way that it reflects light. It's not quite like glass. And then, kind of using this hematite example again, maybe it doesn't look exactly metallic, so it's non-metallic, but it doesn't react with light in kind of a shiny, glassy way. Maybe it looks more earthy, so maybe this is a non-metallic, earthy luster. So there's different ways to describe a non-metallic luster, as you can see from this list, this partial list over here on the slide. And when you're doing the physical property test, you'll look at the mineral, and if it has metallic luster, that's it. If it has a non-metallic luster, then maybe you say to yourself, well, it looks glassy to me. And then when you look at your mineral property tables and you think you know what the mineral is, but the description for the luster is non-metallic, satiny, it could just be some variation in the mineral or a variation in perception. So it's kind of it's more than a rule of thumb, the description of luster, but the point I'm trying to make is not everybody sees non-metallic lusters in the same way, and it kind of takes practice as well. So that's luster. Another very useful test in identifying minerals is how hard the mineral is. How do we tell how hard a mineral is? Do we hit it with a hammer and see how easily it breaks? No, let's not do that. Instead, we define hardness as the resistance to scratching. So sometimes minerals are really hard, and you can use that mineral to scratch other substances, and sometimes minerals are really soft, and they can be scratched easily by a lot of substances. So, but there is a precise quantitative way to define hardness. We use a scale called the Mohs scale of hardness, Mohs hardness scale. This is a table that defines the different hardnesses of minerals. It's a scale of 1 to 10. A hardness of 1 is a really soft mineral, and this list over here and the list over here on the table, they have the numbers 1 to 10, and these are a list of some of the minerals that have that characteristic hardness. That doesn't mean that's all the minerals that have that hardness, and sometimes some minerals have kind of a range of hardnesses, but these are characteristic. So for example, minerals talc and graphite are really soft minerals, so you can easily scratch them. But diamond is the hardest known mineral. It has a hardness of 10, so none of these other minerals can scratch diamond. You can use a diamond to scratch anything else. We do not have any diamond samples for this class. So how do you determine the hardness of a mineral? So let's say you had two minerals that look similar. Let's say they are kind of non-metallic, somewhat glassy luster. Let's use these two examples. Let's say this mineral here and this mineral here. As far as color, they're clear, somewhat colorless. As far as luster, they're non-metallic, and they're both non-metallic, glassy. How do you determine which mineral is which? Well, let's say based on some other property tests you've done, you've determined that one of these minerals is quartz and the other mineral is calcite. So if you look here in this table, or in your mineral property table at the end of your lab, you'll see that calcite has a hardness of 3, which is relatively soft. Quartz has a hardness of 7, which is relatively hard. So these are, I'm not going to ruin these samples by scratching them, but if I were to take one mineral and try to take a corner of it and we're not rubbing, we're just taking the corner and making one hard movement across the other one. Again, I'm not going to use these as an example because these are nice samples and I don't want to scratch them up. But if I were to try to produce a scratch on this mineral, and when I'm done there is no scratch, I don't feel any indentation, that tells me that this mineral is harder than this mineral. And if I know that one is calcite and one is quartz, then I know since this one's harder, it has to be quartz. So that's kind of the basic idea behind it. But you're not, for the most part, you're not going to be using one mineral to scratch another mineral. You're going to be using common objects to perform the hardness test, because not only minerals have a specific hardness, but common objects like your fingernail or a steel nail or something like that, they have characteristic hardness as well. So in your mineral identification kit, you're going to see that you have a couple of these things. You have a steel nail, which in this case would have a hardness of 6, and you would have a glass plate, which has a hardness of 5.5. There is no penny in the lab, but if you wanted to produce a penny that has a hardness of 3.5, there are no fingernails included. With the lab material, you have to use your own. Your fingernail has a hardness of 2.5. So, for example, your fingernail would only be useful in identifying minerals that were softer than 2.5, minerals with a hardness of 1 or 2. So if you were trying to identify one of these 3 minerals or any other mineral with a hardness of 1 or 2, and your fingernail can produce a scratch on that, then that would be very useful. So I'll use this example. So here's a mineral. I want to identify it. So I think, well, maybe this is a soft mineral. Let me take my fingernail, and I'm going to run it over the surface of the mineral. And then I kind of feel it, and oh yeah, it definitely left a scratch. So that's very helpful. That tells me this mineral has a hardness less than 2.5. Right? And that's all it tells me. It doesn't tell me that it has a hardness of 2, and it doesn't tell me that it has a hardness of 1. All I know is that it's less than 2.5. That might be all you need to know in order to identify the mineral. If you're not able to scratch it with your fingernail, then all you know is that the mineral has a hardness of greater than 2.5. So let's say I tried to scratch this mineral with my fingernail, and I can't. It's harder than my fingernail, so it has a hardness of greater than 2.5. That leaves a lot of other hardnesses, 3, 4, 5. How do I know how hard it is? Well, maybe then you say, well, I know that a glass plate has a hardness of 5.5, and I have a glass plate in my mineral identification kit. So if I take a corner of the mineral and I rub it directly on the plate, nothing. So what does that tell me about the hardness of this mineral? It has a hardness greater than 2.5 because it is not scratched by my fingernail, but it has a hardness of less than 5.5 because it cannot scratch the glass. So you see what I mean? You can either try to scratch the mineral with the glass, or you can try to scratch the glass with the mineral. So it's a comparative analysis. So for most of these, you will never actually directly measure the precise hardness. You'll just get a range, and that's probably all you need to know. You know what minerals you have, and so you can look at other properties of the mineral, and with all of that information, you can identify the mineral. So that's hardness. Specific gravity, also called density. Density, the density of a mineral. So density is a property of all matter. It's just the weight or mass of the mineral per volume, as defined, the mass per volume. When we're measuring the density or specific gravity of a mineral, if we're doing it more precisely, we take it into the classroom or the lab setting, and we take the weight of the mineral over a weight of the equal volume of water. You don't need to do that for this lab. We're just going to get a general idea of the density of the mineral. So we're going to talk about density. We're not going to measure it precisely. That's too time consuming. And when you're looking up the density or specific gravity of a mineral in your property table, it will be listed under other properties, I believe. And sometimes it'll just say SG. SG is equal to 5.0, for example. That means the density of pyrite, roughly speaking, is a 5.0, specific gravity of 5.0. So how can we use specific gravity or density if we're not going to measure it precisely? So let's say we have two minerals that look similar to each other. I'm just going to use these two. They don't look exactly alike, but they're both metallic minerals. And if I just kind of heft them in my hand, and I can say easily that this mineral is denser than this mineral. That means if they are about the same size, they occupy about the same volume of space, but this one feels definitely heavier than this one, then this mineral is denser or has a higher specific gravity than this one. So it's kind of a comparative test. So that's density or specific gravity. So here is another property test which is extremely useful, but it might take a little bit of practice to get used to using. Some minerals display this property very readily, others you have to kind of think about it for a while. And this property is called cleavage. The cleavage is how a mineral breaks. It's different than the way the mineral forms. So for example, I've shown you this very nice mineral sample. This is a sample of quartz. You don't see quartz that has this shape very often, because it doesn't form. There's usually, when the minerals are growing, there's usually not enough space for the outward form of the mineral to take the characteristic crystal shape. If you do see samples of this, it's probably not outside. It's probably in some mineral shop, and they're probably going to charge you a lot of money for it. But what were to happen if I took a hammer and break this piece of quartz? Will it still look the same? And the answer is no, because quartz does not display cleavage, meaning that when I break quartz, it doesn't break in a systematic way along planes of weakness. The reason for this is that all of the bonds holding the silica and oxygen together in this quartz are equally strong in all dimensions. So if I break this, it will break randomly, and it would look more like this. You do see some corners on this sample, but there are no repeating flat reflective surfaces on this mineral, so it has no cleavage. Quartz has no cleavage. So these pictures on these slideshows show some samples of what we mean by cleavage. This is a mineral that looks kind of blocky in shape. You see that there's a face here at the top, face here next to it. I'm going to, okay. So here's a face here, and these faces are all parallel to each other. They're all flat surfaces, and they reflect light in the same direction. So we say that this mineral has one, we say that these faces represent one direction of cleavage. There's a lot of faces, but they're all parallel to each other. They're all in the same orientation, so there's one direction here. But then you turn the corner here and you see these other little flat faces that repeat. Here's an example of one. That is another direction of cleavage for the sample. And then we come over here to this side of the mineral and we see another flat face, and it repeats. All these faces are parallel to each other. The faces that you can't see on the back side are also parallel to these faces. So we say that this mineral sample has actually 3 directions of cleavage to it. If this is cleavage, meaning it's not a crystal shape, but it's how the mineral breaks, we can see that this is a side, nice flat surface, and the back side, which we can't see, it's facing away from us, is parallel to it. So that's one direction of cleavage. This face here is another direction of cleavage, and we can't see it, but back here there's another face that's parallel to it. Both of those together are a second direction of cleavage. And then we see a face over here with another parallel face on the other side that we can't see. That's a third direction of cleavage. And then if the ends are also flat cleavage faces, then we say that that's a fourth direction of cleavage. So again, cleavage is the tendency of a mineral to break along flat surfaces, repeating surfaces. So if I were to break this yet again, it will produce the same shape, just smaller pieces of it. And when we talk about cleavage, we have to identify a few things. First of all, we have to say whether or not it shows cleavage, yes cleavage or no. If it does exhibit cleavage, then we have to talk about the number of directions or planes of cleavage. So for example, this example that I went through had 4 directions or 4 planes of cleavage. This one had 1, 2, 3 directions of cleavage. Okay. Let me show you some other examples. This is an example, kind of a geometric representation of one direction of cleavage, and this is an example of a mineral that exhibits that. So for example, this is a mineral. I can actually peel it. This one was already done, but if I were to take a knife or use my fingernail carefully, I could keep peeling this off into kind of sheets like this. So these are all these sheets are parallel to each other. So that's one really obvious direction of cleavage. It might look like it has a cleavage face here, but this is just how the mineral forms. If I were to try to break it along these flat repeating surfaces, it would not keep breaking in the same manner. The only direction in which it cleaves is along this plane. So this is a really good example of one direction of cleavage. If you have a mineral that's very blocky in shape, then you might have two directions of cleavage if the ends of it do not cleave. And then you might ask yourself, so if this is a cleavage face and this is a cleavage face, is the angle between them a right angle, a 90-degree angle, or is it not a 90-degree angle? So you don't have to say that it's not 90 degrees, and as a matter of fact, it's 60 degrees or 120 degrees. You don't have to measure the angle. You just have to recognize, is it 90 degrees or is it something other than 90 degrees? So for example, this mineral that I showed you earlier, it is very blocky in shape, right? It has three directions of cleavage, as most cubes do, or all cubes do. But if you were to look at the angle between the faces, I'm going to try to turn it in such a way, you can see that it doesn't form like square angles. The angles are something other than 90 degrees. So you would say that this mineral exhibits cleavage, three directions of cleavage, but the angles between the cleavage faces are not 90 degrees. Some minerals have three directions of cleavage, just like the sample I just showed you, but they do form nice squares. So here is a picture that kind of shows you that if you keep breaking halite, it'll break into smaller blocks. And the blocks, each one of them have three directions of cleavage, and the angles are always 90 degrees between them. Here's an example like what I showed you, three directions, nice obvious cleavage, but the angles between them, the faces, is not at 90 degrees. And here you can see an example of more repeating flat surfaces. Again, the angles are not at 90 degrees. So cleavage can be difficult to identify because in nature things are not as perfect as geometric drawings or textbook examples, but your samples should be pretty, fairly easy to identify the cleavage in. It just takes practice. And again, if a mineral does not show repeating flat surfaces that are repeating in the same direction, then we say it does not have cleavage. As a matter of fact, we say that it has fracture. It fractures randomly. And I'm going to say that these are really bad examples, these photographs, when we're talking about minerals, because these are not minerals. This is a rock that is not made up of minerals. It's a rock obsidian, which is actually volcanic glass. And glass is not a mineral. It is a solid. It is inorganic. It is naturally occurring. It does have a specific chemical composition, but it does not have a crystalline structure. So it does not fall under the glass, does not fall under the category of a mineral. So glass does not cleave either because it doesn't have a specific chemical, it does not have a specific crystalline arrangement, which means there's randomness. When it breaks randomly. And so that's why it's a good example, but there are minerals that exhibit that same feature, not because they're not crystalline. So for example, quartz, its glassy luster is not made of glass. It's something different than glass. It forms a crystal shape, which shows it does have a crystalline structure. The reason that when the reason it does not exhibit cleavage is not because it doesn't have a crystalline structure. It does have a repeating pattern, but it's because that the bonds are equally strong in all directions. There is no variation in orientation of the chemical structure of this. So that means the bonds are equally strong in all directions. So how it breaks, it won't cleave. It doesn't break along it doesn't break along weaknesses. There are no weaknesses, so to speak. So similar to this. So one thing I wanted to point out again, there's crystalline structure and then there's cleavage versus fracture. Crystalline structure is the way that a mineral forms, the way that it grows. Even if we can't see the mineral, if it's microscopically small, if we look at it under a microscope, we could see that it has a characteristic crystalline structure. Even if it cleaves, it breaks randomly, or if while it's forming, it's growing up against other minerals and therefore doesn't have room to show its crystalline structure on the outside, it still has a crystalline structure interior. Its interior is. And that can be shown if we take a sample, like a thin section slice of the mineral and look at it under a microscope. But once we break the mineral, we're no longer looking at the crystalline faces when we're looking at it with our naked eye, not with a microscope. We're looking at how it breaks. And that's cleavage or fracture, different than the way the mineral grows. Crystalline structure is how a mineral grows, the shapes that form. All minerals have a crystalline structure. Some minerals, when you break them, they cleave and form flat faces. Some minerals, when you break them, they do not cleave, they just break randomly. We call that fracture. So two different things, crystalline structure versus how it breaks. Okay, so I said that there's a lot of other properties that we're not going to look at. There's a couple more properties that I will show you that are not common in that most minerals do not exhibit these properties, but there are common minerals that do exhibit these properties, and these tests are pretty easy to perform. So if we do have that mineral and we do have the tools to perform the test, the tests are very diagnostic, meaning it's really easy to tell the mineral. For example, besides your steel nail that you use for the hardness test, you'll see that you have a magnet in your tool. Most of the minerals that you have will not respond to the magnet, or the magnet will not respond to them. But there are some minerals, when they form, they have the motion of the electrons in the structure of the mineral creates a magnetism. So for example, if I wanted to test to see if this mineral was a mineral that is characterized by magnetism, and I had the magnet just kind of lying in my hand, there's no attraction. It doesn't lift the magnet up. Okay. Some minerals, if I bring it close to the magnet, it will hold the magnet to it. So that's a mineral that exhibits magnetism. And so if you have that mineral, it's easy to identify using a magnet. One more property test. Using hydrochloric acid, you can use other types of acid, but we have a sample of kind of a dilute or weak hydrochloric acid. Will an acid like this cause reaction in most minerals? Yes, given enough time it will in many minerals. What we're looking for is a very instant and obvious example of reaction to this acid, something called effervescence. What that means is if I put a drop of this acid on the mineral surface, I should immediately see bubbles forming on the surface within the drop of acid. And what that tells me is that the mineral having a strong reaction to the acid. There's a chemical reaction taking place in front of our eyes. So there's a group of minerals called carbonate minerals. It's the group of minerals, not the actual mineral name. It includes common minerals such as calcite and dolomite. they will react visibly to acid. Calcite will react strongly to the acid, as you can see in this picture here. In the slideshow, they put a drop of the acid on, and you see these bubbles form, right? Some minerals you might not notice if you're actually seeing air bubbles forming. One thing that you might do is take your nail and scratch the surface of the mineral, make a little bit of powder on it, and then leaving the powder there, then put a drop of acid on the surface of the powder and see if bubbles are forming. But usually you don't need to do that. You can just put a drop of the acid on the mineral surface to see if the bubbles form. Okay, so that is a kind of a quick overview, or maybe not so quick, overview of how to perform the physical property tests on the minerals. Again, the results of those tests, the properties of the minerals are listed in the identification tables. You know what minerals you have a list of the minerals, so you have to perform the tests to figure out which mineral matches to what name.